Swayam Prabha. Digital India. Educated India.
Let's start with this new topic today. We'll look at, I'll split this lecture into two kind of modules, and we'll start with the first module. We'll look at this mathematical modeling part. We'll give overview and context, and possibly see the model of the motor. How do you model the motor? That's what we'll do, and then we will move on in the next module to modeling the friction in the motor. Okay, so we'll talk about friction in lot more details, and see a lot of different aspects of it. So now to begin with, we'll do let's look at the slides. First let me get the pointer right. This is like a rough outline of the entire part, but in the modeling aspect, we are going to look at some of the parts here. Yeah, maybe. So we'll start with these points first, and then actually as we get this context, we'll start about. So why do we need to model? If you think about the models, let us assess the system performance, okay, and then we can develop some controllers. Okay, why they assess? How can you assess this performance with models? Because you can simulate them offline, and without doing much of experimentation, you will be able to kind of get effect of one out the changes of the parameters, or how the system behaves. How do you get all the details about study about how the system behaves and what is its physics. And then further utility of it, for especially for mechatronics purpose, is for development of controllers. So this is there are these two key aspects for development of the model, or necessity for the development of the model. And the criteria for modeling will typically be simplicity versus accuracy. So we want very simple models because we want to develop further controllers. So your partial differential equation models or FEM based models, which are huge matrices and many degrees of freedom, that will be typically difficult to handle in control. So you need to have a simple model, and it should have enough accuracy, reasonable accuracy, to represent whatever physics that we are talking about. And basis of modeling, you all know, we have done a lot of these studies in prior classes, prior courses. You typically model the system based on the physics of the system. Typically in mechatronic systems, you'll have Newton's law, Kirchhoff's law, or many other phenomena. In the fluid mechanics, you may have some laws that may govern the flow behavior, or you may have a temperature behavior, thermal actuator. You want to control temperature. So those kind of models may be there. Okay, so basically they are all based on the physics of the system. And then you may have some empirical methods of modeling. We'll not get into a whole lot details about empirical methods of modeling, but there can be a lot of different models possible just based on the input-output data. You give the input, system behaves in this kind of a fashion, and then you can represent that data by fitting some kind of a model. It need not be just a mathematical curve fitting, but it can be actually a dynamic model which will fit the system. And then that's what empirical model typically will need input-output observation of the system. So for example, if you experimentally get a Bode plot of the system, then one can predict a similar kind of a transfer function which will have the same Bode plot as the system has, and then that is one way of modeling the system. More advanced versions in this form can be in the domain of your artificial intelligence or machine learning based kind of a neurological kind of a neurons based kind of model. Okay, so there is a lot of possibilities in further in this basis of modeling. Then for compliant systems you can, or for more complicated systems, like you may look at like linearized versions of the models. So you have a nonlinear total model, but then you can linearize that model and then use for control. So like that, there are this assumed modes method. There are multiple kind of these methods that would be there in the literature of modeling. Okay, it's a vast kind of a domain, but we are going to look at a part of it which is most important from many motion based mechatronic systems. Okay, we'll not get into thermal systems too much or any fluid based systems too much, but we'll just focus on motion based systems mainly. Okay, and we'll see particularly like the motor model. If we'll get a chance to kind of see this hysteresis modeling in harmonic drives systems based on like some kind of empirical methods. Okay, rather than the pure physics of the system. So this is like typically the outline of the thing. So now let's get talk a little bit more details about these points now. So when we start say the need for modeling, you'll have first assessment of the performance. What is the assessment can be for? Okay, you want to design some system parameters. As a mechatronics engineer, we want to kind of see, okay, what is the kind of sizing of the system I need to do, what are the parameters I should use. So for that you need to study this model and get these parameters and design, and then see that if you have some manufacturing tolerances, I don't have these dimensions coming up to the expectation, they are within some kind of a tolerances, then how I can see that how the system will work or not work, or what is the disturbance that will create in the system, and how do I handle that. Those kind of sensitivity studies can be done by assessing this performance. So you can typically study an output variable as a function of change in the parameter and see the sensitivity behavior there. So if with the change in the parameter, if the output is changing a lot, then that output is very sensitive to the changes in that parameter, and then that particular parameter will need a better kind of a tolerance, strict tolerance control than maybe some other parameters in the system. So that is to assess the performance of the system. And you have, you might have done a lot of these kind of studies of modeling. May not be these sensitivity studies, but like modeling you might have done and seen the changes in parameters. For example, if you take a pendulum kind of example, and I say, okay, if the change in the length is delta, then what will be its effect on some output parameter which you want to control, say for example frequency of the pendulum. So you will be able to kind of say something about that. So that kind of studies can be done with the model. Then you can offline simulate the system and then see its response or behavior to say various inputs, or in the presence of noise, in the presence of disturbances. All these kind of things can be done for the system. So having a reasonable model will definitely help you to study the system in its totality, to expect what you'll expect in the experimental implementation of it. And of course, last very important part is to develop controllers. Okay, so test your performance of the controller, or tune the parameters of the controller, say PID controller, or gains of the PID controller to get desired output for the system. And other important thing is to kind of get a control input history. Okay, you need to make sure that your control input is not getting saturated. We'll talk about this point multiple times, because this is an important aspect that often gets neglected while studying your basic automatic control kind of courses, where we are only focused on stability of the system. All the time we'll talk about how to make the system stable. Are these gains making the system stable? Are these gains not making the system stable? Those kind of things we talk about a whole lot in the automatic control kind of a course. But nobody cares about what is the input that I need to kind of maintain certain performance for the system. Okay, that is very important aspect when you get into the practical world, because always your input is limited. You'll have a saturation on your motor input or motor power that is there, and that needs to get factored into your simulation studies. And for last and the foremost point, you need to remember that you can save substantially in the time and cost if you do good amount of a nice representation of system, and do a lot of things on the soft rather than going in the experiments and doing some stuff without any background in the really modeling. Okay, so there are these criteria for modeling. This is another very important thing. Many times, often people get misled into, oh, I want to capture this behavior accurately. Okay, this model must be capturing all the things whatever are there in the phenomena. So that is not really of interest from control perspective. Okay, we want as simple model as possible, but at the same time capturing all the things that are of interest. Okay, say at different phenomena, if you observe, different things may be of interest. For example, if there is simple block moving resting on the surface, and it is applied by the force, and it is moving under the action of that force. Okay, what kind of model will come to your mind? Okay, if you say, okay, reasonable accuracy, F is equal to ma, that is a kind of a simple model that will be there. Okay, okay, now when you say F is equal to ma, we are neglecting some parts of the dynamics of the interest. It is resting on the surface, so surface would offer some friction as a resistance. Okay, so that needs to kind of get factored in. So then for accuracy, we will need that friction to be accounted for. But now one may say, okay, extending this, okay, oh look, there is a air around the block. Okay, and that air also is giving its resistance. When I kind of start pushing the block, the air is resisting the thing. Now if I start modeling that air resistance to the block, okay, is it of what kind of a contribution to the entire model? Okay, that is one needs to think about that. In some cases this may be of a great importance. In some cases it may be negligible importance, depending upon how fast you are trying to move, or what is the shape of the block and things like that. Okay, so for example, if I am attaching some load on the motor, and that load is rotating, that versus if that load happens to be a fan and I am driving a fan, then that air resistance that comes into picture. Okay, but so now one can think, okay, what is the way I would model such a kind of a scenario, these different scenarios. So for example, if the block is moving with a reasonably low speeds, I don't need to worry about the air resistance at all. Okay, in other cases where there is a fan which is attached to the motor, then I would say, okay, if I start modeling this fluid structure interaction of the fan, and then create some kind of a huge numerical kind of a model, or some partial differential equation based model, it's going to be hell for me to control this fan or this fan system in some way. Okay, if it is needed to be controlled. But then that model will get simplified. Okay, I'll so overall this air is giving some resistance to the motion, and that resistance, if I am able to capture in reasonably well kind of a form, I don't need to worry about. So one can use some kind of a simple linear damping kind of a model, or some kind of a non-linear damping model. Okay, so those are kind of aspects of accuracy of representation of what is a dynamic of interest. Okay, so this is what is an important point or important role for the designer to play, to see, okay, what is an important part in the model, and that often comes by just imagining or actually carrying out some small experiments. Okay, So as we go along, like we can model or we can identify the friction and model the friction in our motor kind of the system. Okay, then there are these empirical models which are based on the so when the physics is so complicated that you cannot capture, as I told about, like a fan which is moving and churning out the air, it cannot, like, the if you go through its real dynamics, it will have, like, a lot of this fluid structure interaction along with some kind of a Navier-Stokes equation, partial differential equations, which will model this physics. I mean, these models will not help us for development of control so much. Okay, so then in that case, we'll consider some empirical models. Okay, where I consider this and overall resistance of the friction to be overall resistance of the air in terms of this some air friction to be of some kind. Okay, some nonlinear kind, and that is like becomes like an empirical model. And I'll identify the parameters of the model such that whatever experimental data that I gather for various speeds, it is fitting reasonably well with this empirical kind of model. Okay, so empirical models understand that they are not based on the physics. Okay, they are based on, like, the input output experimental data, and typically they cannot they do not capture physics of a system. Okay, so then you have this basis of modeling that we talked about. There are typical laws. In addition, you may need to use see the laws of these electrical circuits. Okay, Kirchhoff's law and the Newton's laws. Okay, they typically will be there in many mechatronic systems together. Okay, there will be some kind of a coupling between these two. Okay, we'll see, for example, in a motor model how this coupling happens, and this coupling has a in high speed systems, this coupling has a great effect. Okay, or even in slow speed systems, but in high speed systems, like, there are some effects that are more specifically coming up from the electrical dynamics. In normal, like a lower speed things, then electrical dynamics will not come into picture, because electrons will have flow velocities through the wire much higher order of magnitude than the mechanical motions in the system. Okay, so electrical dynamics will really not come into picture unless, like, these speeds of motion of electrons, or, like, some of the electronic elements that we are using, say your magnetic actuators or something, has some dynamics, so that this electron dynamics matches with the frequencies of mechanical motion. So mechanical motions need, for that matter, to be very fast to have electrical and mechanical forces which are competing now with each other. Otherwise, like, some simple electrical dynamics will not need to consider, but some kind of simple relationships will be sufficient. Okay, we'll see this point in more detail when we see the model for the motor. Then you can use some additional, like, physics in the system and things like that. So for CD-ROM case, for example, you may need to kind of think about some small consideration about the, like, Gaussian beam propagation and laws of optics there. Like that, many other kind of physics may come up. Okay, depend upon what system you are handling here. Okay. Then based on input-output observations, like, it will be based on experimental observations. You carry out many different experiments and gather, like, the data of about these different complex phenomena. For example, hysteresis or some chemical processes, fluid dynamic systems. They are kind of very complicated to model from true physics of them. That's where, like, you just give some input data and observe the output, and then start looking at the models which can represent that data. These are the typical steps in modeling. Okay, so first, as we are mentioning earlier also, identify the important physics of the phenomena, and you may do little bit in iterative way this step, or if you are experienced, you may kind of, like, directly jump on to kind of knowing, okay, this will represent my physics of the model very well. And then the major decision to take is whether to go for empirical models, which are input output based models, or you want to model like completely physics. This is an important decision to take, and then once you take this decision, you apply corresponding laws and get your models done. So this is how we'll proceed to do the modeling step. Now we'll see a motor model, so that we apply now these whatever things that we have gathered, overall kind of a context of modeling, we'll apply it to this motor system now, and see. So this is a motor. At the back, what you see here is an encoder for the motor, and then there are these wirings for the motor whose terminals are given in that data sheet, and there is small little gear sitting on the shaft of the motor here. So this motor will try to kind of see whether we can model this motor or not. Okay. So we'll work with some simple models of the motor to begin with. We may make it a little bit of a no, maybe we can work with the simple models only. I think we'll not get into more complicated models for motors in terms of any other kind of motors. I mean, we'll stick to the DC servo motor kind of a model. Okay. And later on we'll see some other actuators as a solenoid or other kind of actuators. Now just pause here for a moment and think, okay, how do you model this motor? What is the physics that is going on inside? Okay, what kind of a ways that can be captured into some kind of a model? So think in terms of the separation in mechanical and electrical domains. Okay, what is happening in mechanical domain and what is happening in electrical domain? So for example, in electrical domain, you are giving some supply to these lines to the motor, and motor is receiving some voltage signal, and it is exciting its coils. The coils, when get excited with the magnetic, they are suspended in typically in the permanent magnetic field, and when the current is passed through the coil which is suspended in a permanent magnet, you know that by Lorentz law you'll get a force on that coil, and that force will cause the motor to rotate. That is what is going on as a phenomena, I mean as a physics in the system. Now we want to model this physics. So what is going to happen? How do you kind of think about modeling this motor? So let's kind of get a mechanical domain separated with the electronics domain and see through, okay, what are the laws which will work at mechanical. So mechanical domain, what happens here? Can you think about? You'll see that because of this current that is flowing in the wires, the force is applied on the wires. So there is some kind of a torque that is generated inside. Okay. So now there is a torque on the mass which is now rotating. So it's similar kind of a situation as if the block is lying on the surface, okay, and applied by the force. Okay, it's the same situation where now it's only in the variable of theta, or motion of the motor. Okay, so the torque is applied on the system of some mass. Okay, and there is some bearings are there to this mass. So like that we start and model the mechanical dynamics. Okay, so see what are the resistances that are provided. The generation of the torque is say motor is generating torque which is tau m, and like that you can start yourself first to write some equations. Okay, so do that step, you write your own equations in mechanical domain. Think about electronics domain also in the similar kind of a fashion, and then we see, okay, in electrical domain what all equations or what all the elements in the electronic circuit we need to consider. So you are applying voltage, so voltage source is there. Then there will be some resistance that will be applied by the wires. Then since the wires are in coil form, there will be some inductance that will be there. So like that we can think about these different elements that will be there as a part of the electrical circuit and start modeling this motor. Okay, and then once you have finished your own kind of things, then you kind of proceed from this. So pause at this moment, I would say, and then once you have done something on the paper, then you can proceed to the next part of the lecture. Okay, so here you have representation in the form of an electrical circuit and in the form of a mechanical free body diagram. Okay, that's what we do for any mechanical system. Okay, so you can see that here that the torque that is applied here will have will be through the motor wires, windings. Okay, that is like motor torque, tau m. There will be a torque for generated by the motor, and then there will be motion in the same direction, and then you have some resisting torque which is given by the viscous kind of a friction. And the important aspect here is in the electrical domain. Okay, so so important aspect is like where is the coupling. Okay, what is the coupling between the electrical and electronics or electrical domain and mechanical domain. Okay, say for example, if you see this torque that is getting generated, as we have seen by Lorentz law, the current is related to this torque, right? So this torque will be proportional to the current that is flowing into the motor windings. And similarly, if you see in the electrical domain, you will have the resistance, inductance, and then there will be this back EMF that is generated. Do you know what is this? This is because, like, suppose you don't apply voltage and you rotate the motor shaft. Okay, when you are not applying any voltage and rotating the motor shaft, if you see the terminals of your motor wires, they will show some voltage. Okay, there is like a electrical conductor placed in the magnetic field and it is moving, it will generate current. Okay, that we term as a back EMF. And more faster you move the motor, more will be this current that is generated, or this back EMF that is generated. Okay, so this is back EMF is proportional to this theta, theta dot, sorry, of velocity of motor shaft rotation. Okay, so these are the two areas of the coupling. Coupling from mechanical to electrical is through this back EMF, and coupling from electrical to the mechanical is through the torque that is getting applied, which is proportional to tau I. Current torque which is proportional to the current that is flowing in the motor, proportional to the current I. So now how do you write the equations? So if you check here, whatever your equations you have written, have you missed anything? Probably you might have missed this back EMF part. Okay, so you add that back EMF part and see what is your enhanced model, and then you move forward. Okay, then you'll see that you'll get some equations of this kind. Okay, so now here this so mechanical domain we apply J theta double dot. Okay, so J is the inertia of the mass moment of inertia of the motor, whatever is rotating in the motor shaft, along with the motor shaft. Theta double dot will be acceleration, angular acceleration. Then Bm theta m double dot is resisting torque because of some kind of a bearing friction, viscous friction in the bearing. And then if you are applying some additional load on the motor, then this tau I, and there is some gearbox also. Okay, the load is not directly applied on the motor shaft, but it is applied through a gearbox which is having n as a gear ratio. Then you will get this tau I upon n term here, which is equal to tau m, and this tau m is the torque which is generated by the motor. So you need to be careful about the torque which is applied externally on the motor, and motor is working against that torque versus the torque that is generated by the motor. Okay, this is the torque that is generated by the motor, typically is proportional to the current that is going into the armature windings. And this is like a constant factor. This phi is a flux of magnetic field in the permanent magnet motor. That flux will be constant. In the separately excited motor, there is no permanent magnet there. There is a magnetic coil, okay, through which the motor permanent instead of creating permanent magnet, you create a electromagnetic magnet there. Okay, so that flux will be varying. It may change. Okay, so we are not talking about separately excited motors. We mainly talk about permanent magnet kind of a motors. So this both the terms can be a single constant. Okay, and in the electrical domain, if you see now, the voltage that is applied to the motor is consumed in the resistive losses IR, and then back EMF, and then in the inductance of the motor. Inductance of the motor is, if it is L di by dt would be the part of the it's not a resistance, it's some kind of a fluctuation of the voltage across the inductor. Okay, and according to that your complete balance of the voltage will take place, and then this is a back EMF that is in the system, and as we know, the back EMF is proportional to the speed omega. Okay, so you can write it as again, this flux may be showing as a separate component or may not show as a separate component, depending upon permanent magnet motor or separately excited motor. Okay, so this is a basic kind of a motor dynamics model. Now one can simplify this further by considering this coupling of the current. Eliminate the current and you will get some more simplification for the model. So you can work about that and see, okay, how you can get a unified model of both these things considered together, or all these relationships considered together, and you get the entire equation of the motion of the motor. Okay, that may have this L di by dt term coming. So typically, L inductance of these motors is very, very low. So many times, for all practical purposes, this inductance is neglected. Okay, so this electrical dynamics, as I was saying before, that it is very fast dynamics here. So that dynamics is seldom kind of affects the mechanical coupling effects. It doesn't matter really. So there are two things. Although this current may be changing so fast, if the low inductance of the motor itself, the motor winding inductance is very, very low value as compared to this back EMF or these voltages that are given here, other quantities of the. So this term gets neglected in the actual representation practically. So with this term there or not there, you can kind of try to see what is the motor model equations look like, and then you can kind of take some example and simulate also. Okay, they have some kind of you go to this Maxon motor website and take some motor and put some parameters and check out, and then those kind of exercise will be nice to do, to see, okay, how this motor will have different effects coming up in the modeling. Okay, now you need to also now we'll do this exercise, but so based on this model itself, we can get the realistic simulation for the motor done. Okay, so we can do that without adding any load. Okay, so we don't have this term tau I upon n. We're not adding any load on the motor. Okay, that gear is just sitting on our motor, but if you apply some, you put some linkage there or some kind of a mechanisms there, then that is additional load that is coming up. But currently, right now we'll not be considering that any external load to the motor, and then we can start thinking, okay, how do we can identify the parameters of motor. So we'll just think about this. Okay, given this now, the motor model, what are the ways in which one can kind of see and identify, okay, what is, say, for example, the inertia of the motor. So consider these equations together and think about this. This is very important and nice thinking that you can have, to say, okay, I want to say get inertia of the motor. What I need to measure. Okay, what sensors you have on your motor to measure is the encoder. So encoder data, if I measure, can I get these parameters? That is the kind of a thinking one can go ahead and do. then typically there will be a friction in the motor. Okay, so right now whatever we are modeled, we have not considered friction in the motor, but when we are doing this parameter identification, and there will be a part, friction will be part of that identification process also. Okay, so that will be coming up here. Okay, so you need to be aware about that, and then now we'll have a question. Okay, how do you model friction? Okay, so we'll discuss now in the next module in a great detail, like, what is the friction and how do you kind of model friction and represent friction in the motor model. And then we'll be able to see a little more about this friction knowledge of having this good knowledge of the friction and the model of the friction is very, very important aspect for mechatronics engineer to consider or not consider friction, or take some decisions based on the situation at hand in terms of friction. Okay, so we'll do that now in the next module. So I'll stop here for this module.